So, um, you hear me well, right?
Yes.
Okay, so welcome everybody to the first Web Coffee of Intelligent Project. Thanks to Alex for organizing and asking us to have this cool concept. We are fortunate actually to have a nice guest from the US, from Johns Hopkins University, also to hear us what we are doing in intelligence. We have also some students here. At the end, you can see not much audience, but I guess in-person audience is enough for today. The quantity is not important, the quality is important. So the concept actually is to have around 1 hour discussion about the project. I would start with the general overview of the project and then what the University of Cologne contribution is. So after me, Hossein and Tom would share with you with more technicalities that we are doing in the project. And feel free to interrupt us in the middle of the presentation. It's a friendly conversation on what is happening in the project after around it's 60 months, right? So we are almost in the middle of the project. If you consider the project is a 3-year project, uh, this is, as you know, I'll repeat it for the audience here. It's um, EU Horizon Research and Innovation uh, funding, which is called Interoperable Tools for Network-Aware Ledger-Based Local Energy Sharing and Flexibility Management Leveraging User Engagement, and short for intelligent. Um, this has been started in December 2024, and we expect to finalize it in November 2027. As I said, we are right in the middle, and the cons you should actually.
Yeah.
So the main core of the project is actually to shift the energy sector from passive consumer to active consumers. This is the core of the concept. And what we are facing currently as issues is, this energy crisis that we are facing here and there because of different externalities. There could be war, there could be different um, problems that lead us to the question, if we are gonna still use not only fossil fuel based generation, but also the bulk power plant. Are we all also still using the bulk power plant, or do we want to be locally self-sufficient in order to avoid this kind of problems raised by this energy crisis we are facing, especially in Europe, with the scarce of, good resource of energy, actually. And then the other problem that most of the European states are facing is the pricing mechanism. It is mainly, especially in Germany, it is mainly single zonal pricing, which has caused the problem of congestion management pricing. There could be something similar, but we cannot do the exact same nodal pricing. We need to have something adaptive, suitable for the structure of the current, framework of electricity marketing in Europe. And the concept that we are thinking about with other experts is the local pricing. And the local pricings are going to be actually developed within the cities, within the energy communities. And this is actually another issue that could lead us to the project like local markets, local flexibility, and energy markets. Um, then there's other issue that is a kind of barrier for us to have the local generation and local market and self-sufficiency.
Oh, yeah.
Getting, and we are still in the previous slide.
Okay.
So this is the passiveness of the citizens on the interaction with the market, with the energy usage, and things like that. So we need to actually make the citizens more active, especially who has different energy assets. So nowadays you see that the rooftop PV panels are going to be trendy. Everybody, most of the people are trying to install it, especially encountering this energy crisis. This would be actually more popular. People are going to get this um, energy assets to be at least a little bit more independent from the power system for the whole electricity network. And this is some sort of good opportunity to make the citizens active, and we need to have some measures to be taken for using in a positive way this activeness. So also in the line with the climate neutrality objective, and also EU targets up until 2030 to use the clean energy, we have the opportunities, we have the nice opportunities as concept for energy communities. This is a cool, actually, possibility that EU has been given for developing more and more different type of energy communities in which we can run the market inside it. It could be local energy markets or local flexibility market, meaning that the coordination of these assets, ranging from PVs to the maybe charging stations, those could be coordinated in a market aspect, so that this price signal could decide which asset should actually generate, which load should be consumed, and this demand response, demand side management could be coordinated via the market signals. And then, speaking of this zonal pricing, these kind of energy communities, these kind of local markets, they could help us developing the local prices, which could resolve in the future the problems of single zonal pricing to be shifted towards the local price. And then, needless to say, the congestion management using these flexibilities and using these local prices would be much easier, and we are supporting the grid stability. Yeah. Having said that, 2 years ago, we decided to apply for this project, which is a very practical project to develop various tools, various practical tools, and to be tested and demonstrated in real world to see how these gaps are going to be actually breached. So in terms of this consortium is a very nice consortium with different stakeholders from industry, from academia, and from technology and innovation. So in academia, we have, except us, we have Technical University of Munich, also AIT as a research institution in Switzerland, HSLU from Switzerland, and University of Galway. And the rest, there are more industrial spin-offs, and the pilot sites. So in terms of the pilot site, which is actually very cool for us, because eventually everything is going to be tested in these pilot sites as energy communities. They are real energy communities, even though they are small scale, but they will help us to see what is the reaction of our design to this small scale situation in practice. So we have one island in Irish Island, Ireland Island, as one of these pilot sites. There are each and any of them have different characteristics. So one of them has a more robust grid. The other one, for example, the Iron Island, because of the severity of the weather, they have more outages. So the grid is not that stable. So it's a feature we want to discover in this kind of self-sufficiency, how the reaction of this pilot would look like. And then we have Portuguese pilot site with different industrial and also residential customers. And they are also, there are some challenges for this pilot site, which is going to be resolved during the course of the project in order to see how is the reaction of industrial, the pilot sites. And the scale is also very small, and we need to see what is the reaction of actually these markets with that illiquidity to such a small scale community. And we have two Swiss partners, Luzern, and one in Luzern and the other one in Lugano. The Lugano is 15 residential households. This is some sort of a different pilot site because the customers are different in terms of their desire to be involved in such a market or such an ecosystem, so to say. And then we have Luzern is also a smaller scale. There's large buildings, there are apartments, and the problem for this pilot site was that you have just one rooftop PV system for the whole system. And this is going to be actually modified to be more suitable for the whole, market and energy trading or energy exchange concept. So these are the pilot sites, and we are excited to have them for further demonstration. But the whole concept of intelligence here in this infograph is going to be shown, right? So it is a bottom-up solution. Therefore, we have the household, and this doesn't need to be necessarily a household. This is just a symbol to be shown how the customer is going to be shaped as a community member, right? This community member, which is right now here, the residential prosumer, they have different energy assets with different digital infrastructure, and each and any of them would be equipped with the smart energy management system. And this project is both, we will talk about that later, in a sense that the whole energy use would be managed by this system, and the citizen and the owner of this or the residents of this residential, they have some user interface as application to insert the inputs, for example, their preferences and the other inputs that we are defining for them to system, but within their preferences. So you see that we need communication, we need, for the methodology wise, we need different maybe optimization, AI algorithms, and so on and so forth. Therefore, the whole community would be shaped as a market ecosystem to exchange energy among each other, so that we assume that each household, each residential or commercial customers or members are going to be equipped with these facilities, and then eventually they have the possibility to share energy and manage their flexibility among each other internal. This is actually very important. And what is very important for us as a customer-centric or citizen-centric solution is to have first initially analyzing the behavior of the customers. So what was done initially in this project was to collect the data from the pilots in order to understand and analyze what is going on in terms of energy usage, and also doing some surveys in order to analyze the customers and prosumers' behavior, so that we can use these the results of this analysis for designing and developing the user interface, market platform, and energy management system. So we started with the socio-economical analysis, like what is the exact behavior or what is the expectation of the behavior from the pilot size we have. And then technically, we have three different tools. The first one is a trading tool, which is a marketplace, and it includes the energy trading and flexibility management, meaning that everybody can share their energy, and then they can also contribute and provide flexibility. So this is the platform that actually give the incentive as a price as incentive for the prosumers to trade different actually as energy and flexibility concepts. And then most importantly, the communication is important. So the communication and data exchange, we have the platform for that. And this is actually based on different cybersecurity issues. This is designed based on many security issues, and also it is going to be protocol agnostic, and also it ensures the interoperability between different tools. And finally, the optimization, which is the intelligence part of the work, would be the force, flexibility, and optimization service. And we are designing the AI powered algorithms for this specific tool to make the citizen some sort of giving the automation to decide how to be in the market. So this is the sort of empowerment for the citizens from our side, that without further or too much of effort, they can exchange electricity and provide flexibility. So what is our contribution? The main contribution for us is in two tools. So the trading tool, we are developing the automated market maker-based mechanism, and using also network-aware algorithms, using the grid constraint for energy trading, and also for the flexibility market. And the other part would be the flexibility and optimization service. We are contributing in many aspects of this tool, also a prediction module, flexibility estimation module, co-optimization, and also the trading module. So with that, actually, I would like to invite my colleague Tom to further explain the technicalities. But before that, there's another slide.
Yeah.
Yeah. Before going to the more technical aspects, I would like to also, there are some questions with the project. Why we are doing this project, right? There are some aspects need to be read out. So for example, what is the path for being shifted from the centralized market towards decentralized market, or the peer-to-peer market? And what are the impact of the data, blockchain, and also, these cybersecurity things? How secure should be this data? This is very important issue in not only in Europe but worldwide. What could be this cybersecurity measures to be taken in order to have the reliable platform? And then how the local market is working. We are gonna describe it a little bit in a bit. The other cool aspect is the energy communities. So it is expected by 2030 that the energy communities would cover at least 10,000 population. So this is what is going to be expected for the future of energy community. But we feel this concept has somehow further much more potential to be leveraged and unlock the flexibility and also empower the citizens for being more active. So with that, I would like to have Tom for more explanation about the market.
Okay, so as Saber mentioned, obviously to have the local pricing, we need a market mechanism to facilitate this. And there are existing mechanisms, which two of them we will also be testing in the project. But alongside this one, we will implement a new one, or are actually in the process of implementing one. But first, let's look at some existing ways to do trading, so to say, in general. And obviously, we have order book-based mechanisms like batch auctions, single auctions, double auctions, where users send a bid or an offer with the price and the quantity of whatever asset they want to buy. Or we have other mechanisms like negotiation-based mechanisms or equilibrium-based mechanisms, which have their pros and cons. But there are some issues with the existing ones which motivated us to get inspired from a different domain, which I will get to in a minute. The first one is obviously that many of these mechanisms, for example, the order book-based ones, struggle with low liquidity markets. So this means markets with few participants or very few orders, you will end up having large spreads or large distances in the order books between the orders, and therefore have high slippage and very inefficient pricing and high transaction costs as well. And the second one is that the other mechanisms that maybe don't work with an order book rely on some centralized entity to manage the market. So in that sense, they're not really peer-to-peer. So we need some mechanism that combines these features and in the end provides good prices for the citizens and has a fair market that incentivizes participation in this market. And the domain where I come from is actually decentralized finance and cryptocurrency markets. And interestingly, they faced a very similar issue. So in cryptocurrency markets, you have a very long tail of unknown cryptocurrencies that have few people trading them. And in the beginning, when this trend started, they also tried to implement decentralized order book mechanisms, which, as I explained before, didn't work really well. And then a new concept was born, which is called the automated market maker, which provides constant liquidity and prices based on a function that is based on the supply to demand of the assets that are being traded. makers work. Essentially, they're managed by a so-called smart contract, which is just a piece of code running on the blockchain. And people can provide liquidity of the two assets they want to trade. In our case, it would be energy against money, basically. And then people can trade in and out of this so-called automated market maker, have constant liquidity that is being provided by these so-called liquidity providers, and they get paid based on the fees. However, using this exact mechanism doesn't really translate to the purpose for energy markets. So because the markets function a bit differently, for example, in our case, we need a discrete auction because we have these auction windows. So we're not having a continuous market like a classical AMM would work. And this leads us also to a few other design requirements, so to say, that we need for our market is that it needs to be decentralized, truly peer-to-peer, which an AMM could cover. And finally, we need a fair price. So fair in that sense that it needs to be fair for producers and consumers as well to provide the incentive to participate in the market and be a nice alternative to the outside market. And that basically leads us to the idea of our concept that we're developing, which we're calling AMMBA, so Automated Market Maker Based Batch Auction. It combines features of both batch auctions and automated market makers. So we're having discrete auctions every 15 minutes or so, where buyers and sellers can submit their orders. And the nice thing in our case, because we're using a function to price the market and not matching the orders in an order book, means that we're alleviating this burden from the end user. They don't need to think of a price that is for their energy. The function will take care of that and find a fair price. So they submit their orders. These orders get batched together, like it would be the case in a classical batch auction. Then we have this function, which I will get to on the next slide, which computes a uniform clearing price. And then every participant paid in this auction gets their share of energy based on how much they need or how much they sell. And finally, these trades are written to the blockchain, so they're fully transparent and immutable. And that is also one requirement that we have. So price function. The nice thing about a peer-to-peer energy market is that we have a clearly defined range of prices that make sense, actually, because we for sure want the price in our peer-to-peer market to be in between the feed-in tariff and the retail energy price. Otherwise, the people would choose those options and not participate in our market. So that's why we came up with, we're utilizing this kind of sigmoid function that is basically just in between those two prices, which we would set, or the community would set for based on whatever their feed-in tariff or clearing price or retail price would be in their market. And then we have these parameters that we can change to change the shape of the function, as you can see. So it might be that one community wants to incentivize the production of energy and building new PV panels, for example. And that's in that case, you would want a higher clearing price, so people would get incentivized to produce more energy, right? And these parameters basically can change that, and they would be whatever governance the respective community has. They could change those parameters to adjust for whatever their needs are. And that leads us also to the second thing, which is preference management. So as Sabra mentioned, there are some preferences in several communities. For example, there is the need for a preferred trading partner. Imagine next doors, maybe you have a kindergarten, and instead of selling your energy in the peer-to-peer market, you might want to send this energy to this kindergarten for free, right? So our mechanism also will enable this feature. So you could, with each trade, you can say which partner you want to trade with, to what price, or if you want to even assign a price at all. And if that's mutually agreed on, then our mechanism would basically match those orders before they would go into our AMM mechanism. And the second one is The subsidy of green energy, for example, would be managed via so-called energy type multipliers. So imagine you have a community that wants to incentivize also the production of green energy. In this case, we would calculate the clearing price as before. Let's say we end up at the price of 20 cents. Then the community maybe agreed to subsidize it with 20%. Then the people producing green energy would get 20% more revenue, and it would be financed by people who maybe buy or sell gray energy, right? Because it needs to be zero sum. But yeah, that's the basic idea, to keep the liquidity and to also account for preferences. And finally, of course, each market mechanism needs to be incentive compatible. What does it mean? It basically means we want a market mechanism that's robust against gaming it or manipulating the system. And in theory, there are two ways to do it. For example, imagine we don't have enough supply, so there's more demand than supply in our market. You can imagine some powerful energy producer could, in the auction, withhold some of their available funds to push the price up, to make the supply even more scarce, and then sell it at a higher price to profit from this manipulation. And if you mirror it the other way around, it works as well. So if we have a lot of supply, little demand, someone could signal that they need less than they actually do to drive the price down as well, and then buy more energy and profit from this. And our solution to this is a penalty mechanism where we basically calculate the what if price and calculate what the harm to the other participants would be. So let's say we see that someone actually sold way more energy than they initially signaled that they want to sell in the auction. And we see from the smart meter data that they fed in way more into the grid, then we can calculate this penalty. So for them, it's not profitable to do these kind of schemes, and everyone else gets compensated for the potential damage from this market manipulation. So step by step, it would work that we would first check, do we have a supply or demand limited round? So is there more supply or more demand? And then compare the energy sales in the auction, which we can see in the trades that occurred, against the smart meter data after the energy delivery occurred. And then we mark everyone who basically has a very large deviation and penalize them based on the mechanism that I explained, right? We calculate the what if price and the damage cost to each participant, and then we penalize the other ones. And this basically guaranteed that the smartest way to participate in this market is to be truthful and honest. So even that we assume that in our pilot sites, obviously there would be no one gaming the system, you need to consider this, and this makes this mechanism robust against such games. So how do we implement this technically? Just to go briefly into it, we have basically three main modules. The off-chain database is a separate module that is shared across different services, which is kind of the central database for each pilot sites, where we track orders, trades, measurements, among other things. And for each auction window, the way it would work is that our AMM clearing node would collect all the orders that the different participants submit for this market window. And then all the demand and supply that is needed would be aggregated and sent to the smart contract, which calculates the final clearing price in the way that I described before. And then we would resolve, okay, this person gets this much energy and pays this much. And this would happen for every participant. And in this step, also the preferences would be considered. And then let's say some time passes and the market settles, the energy delivery occurred. Then we would actually gather the real smart meter data, and we would see the deviation between what was traded and what actually was fed and consumed from the grid, and apply the penalties, as I mentioned before. And yeah, we also have some evidence that our market mechanism may be optimal for such a case, because in our forthcoming paper, we did a simulation with data from 1,000 synthetic households, which was based on real and we used Portuguese prosumer tariff types. And the settlement cycle was 15 minutes, as I said before, and we compared it against a classical double auction and a uniform price auction. And to even see like how does our performance change based on how many prosumers we have in each market, we simulated it with in 3 scenarios. So a low prosumer penetration scenario, which is like 30% of households also produce energy, then 56% and 86%. And indeed, our market mechanism in terms of all kinds of metrics always performed pretty well, even either very close to optimum or as the best out of those 3. So for example, you can see for the total welfare, so the sum of the profit and the utility that was produced, we outperformed the other mechanisms. And the same is for other indices like the community self-consumption, which was very high, and equality index as well. And so, yeah, we have initial evidence from our simulation that our mechanism could perform really well, but we hope to see this also happen in the real energy communities and the real pilot sites. And here you can see how such a price would evolve. This is from noon to noon, right? So, and you can see the top row is our function, which is a very smooth clearing price and very correlated to obviously the supply to demand ratio, which we would want. And the lower one is the classical order book, which you can see has very erratic price movements. And yeah, this is simply based due to slippage and maybe large spreads and orders in such a small market. So we have some evidence that our mechanism could perform really well and produce predictable revenues for prosumers. So hopefully we have sustained participation and yeah, nice participation in these peer-to-peer markets. And because we use dispatching of orders, no single order can swing the market really well. So that's also a nice feature of batch auctions, that an aggregate batching of orders smooths outliers, which I will also get to in the next slide. And we always have an optimal price in the sense of that the price is always cheaper than the retail electricity price and higher than the feed-in tariff. So it's a win-win situation for producers and consumers in such a market. And finally, of course, you could ask yourself what happens when, because the trading is based on the forecasts of energy consumption and production, and these algorithms won't be perfect. So what happens when we have deviations? We tested that one as well, and fortunately, our algorithm is also very robust against those. Like the metrics don't change very much, and this is basically also a feature of this batching mechanism, because we don't price based on individual bids and offers, but on the aggregate supply to demand ratio. So these small errors are often then adjusted for. Okay, so this was the focus is now on how do we actually provide those forecasts, and Hossein will take over here.
Thank you.
Yeah, thank you, Tom. Now I will briefly present 2 topics that we are currently working on. One in work package 4 of the project and the other in work package 5. One of the main goals of the intelligent project is to enable end users like households to actively participate in automated and decentralized energy trading and flexibility markets. And to achieve this goal, the project has introduced flexibility and energy optimization service, or FOS tool, that allows to employ the flexibility of a small-scale distributed energy resources considering the operational constraints of these assets and also the user preferences. FOS includes multiple functional components together, enables local energy community members to participate in peer-to-peer energy trading and flexibility markets. As we can see in this figure, we can see the interactions among the four main modules that we have in FOS, including prediction, optimization, flexibility estimation, and trading modules. In this tool, AI or ML-driven and advanced optimization are employed to forecast, optimize the energy scheduling, and to determine the bidding strategy of committee members. And additionally, it enables users to integrate their preferences into the energy assets and trading strategies, and it enables us to fully utilize the automated control with transparent and user-centric operation. And finally, FOS enables distribution system operators and the energy community operator or manager to mitigate the grid congestion using the flexibility available in the local energy community members. Now, I briefly introduce these four modules that we have in the FOS architecture. The prediction module that mainly focuses on the short-term forecasting of key parameters, including the electricity and heat demand forecasting, renewable generation that we have in the project, PV generation, and run-of-river hydropower plant, and market-related signals like the volumes of energy traded or flexibility services and their associated prices, and asset-related information like the asset degradation and, for example, EV availability. And for the optimization module, the main goal is to compute the optimal scheduling of energy assets and accordingly the imported and exported profiles of local energy community members. And the main energy assets that we have in the intelligent project include the PV, run-of-river hydropower plant, battery energy storage system, EV charger, thermal energy storage system, heat pump, and electric boiler. That the main goal of the optimization module is to determine their optimal scheduling. And we have different type of objective function in the optimization module, but now we are working on the minimizing the total operation cost of the committee members, and we have technical and user-specific constraint in the optimization module. And also the next module we have is flexibility estimation module that quantifies the available upward and downward flexibility potential of the local energy committee member that enables them to participate in flexibility market. And also in this module, we calculate and estimate the cost associated with providing flexibility. For different values of flexibility, we calculate its associated cost that we need this to enable committee members to participate in the flexibility market. And finally, using the output of prediction module, optimization module, flexibility estimation module, we have trading module that enables the participation in local market using the automated machine learning based bid generation. And the bid generated aligns with the user preferences and the system objectives. In this project, we have proposed two approaches to determine the optimal operational scheduling and flexibility potential of market participants. I mean, for optimization module and flexibility estimation module, the first one is sequential approach, that in the first step, we run an MPC-based optimization with the objective of minimizing total energy procurement cost of the community member. We have some constraint in the optimization module, like the asset operational constraints and the power flow, the thermal and electrical power balance constraint. And also then we calculate the optimal operational scheduling of energy assets in the next step. That in this regard, we run another optimization problem that the objective function is maximizing the available flexibility, and the constraints include the technical and user-specific limits of the energy assets, and also the thermal energy balance for the thermally coupled assets like the heat pump, thermal energy storage system, and electric boiler, because we don't have any thermal grid exchange in the community member. And the next approach that we propose is co-optimization approach, that instead of running optimization and flexibility estimation separately, we run a single step model predictive control based optimization for joint scheduling and flexibility estimation of the energy assets. The objective function is to minimize the total cost, that we consider the revenues of flexibility in the co-optimization approach. And to calculate or to estimate the revenue of flexibility, we need to have the forecasted prices of the energy and flexibility markets, as well as the flexibility enabled and utilized in the flexibility market. And we have different types of constraints in the co-optimization problem, like the constraint associated with the energy assets, the power balance, and also the equations for the coupling between asset scheduling and flexibility provision. Here, I want to present some numerical results that we have for comparing our proposed model, the co-optimization model and the sequential approach. We have the optimization problem that is mixed integer linear programming, and we solved it using GLPK solver, and we utilize the OpenToonFlex dataset for the distributed energy resources operational parameters, and for the market data, we utilize the Australian national electricity market data for the energy market, and the regulation FCAS markets for the raise and lower, because we didn't have the data for the flexibility market, for the local flexibility market. And the results show that although energy procurement cost in our proposed model compared to the sequential approach is slightly higher, but it is compensated by the increased flexibility income. As we can see, the co-optimization approach has the around 36% higher flexibility revenue compared to the sequential method. And overall, these results show that our proposed model, the co-optimization model, has around 25% saving compared to the sequential model, because of the higher amount of revenue that we have from the flexibility market. Another topic that I want to present is grid modeling in blockchain-based energy trading. Actually, this is part of our research in the incorporating the impact of the energy community networks in the automated market maker-based batch auction mechanism. And in the peer-to-peer energy trading studies, and in the peer-to-peer, local energy trading, accurate grid constraint modeling and fair loss allocation are important aspects of these studies. In the studies, we have two different approaches. The first one is off-chain approach, that the network constraint and the loss allocation are modeled outside the blockchain, outside the smart contract. And we have the optimization engine or third party to calculate the power flow model. And we have advantage, benefit, and disadvantages. The advantage of this method is that we can utilize the AC power flow models, and so we have accurate results. And the main disadvantage is the lower transparency and lower trust compared to the on-chain solution. On-chain solution is that these kind of power flow models enable us to model power flow equations in the smart contract. The main advantage of this category of models are fully transparent and trustworthy that we have from the blockchain platform. And the main downside is that we require simplified power flow models because of the computational limitation that we have in the blockchain platform. The main limitation of existing on-chain models in the papers include fixed voltage assumption. They mainly consider the 1 per unit for the voltage magnitude, and they mainly neglected losses, or they utilize the simplified and often unfair loss allocation in their proposed model. So we utilize the on-chain power flow model that we can utilize this model for the radial distribution networks, and we don't have the assumption of 1 per unit voltage magnitude. The only assumption simplification that we have here is that we assume that the small angles are, the voltage angles are small, that it's rational for the distribution network. And this assumption allows us to utilize a virtual variable in solving the power flow equations, that we can eliminate the nonlinearities that we have from the losses in the equation, and then we solve the problem based on the virtual variable. We can convert them into the real variables. And we utilize this approach that we can have the lower complexity, so it is blockchain compatible. And also, I showed the result in the last slide, that the result of the on-chain power flow matches the AC power flow. That is the most accurate model for the power flow modeling. And for considering the distribution network constraint, we propose a corrective action model that we run an optimization problem with the objective of minimizing the required adjustment to alleviate the voltage and power flow constraint violation in the AMMBA energy trading, and to solve the optimization problem in a decentralized implementation. We utilize the Lagrangian relaxation, that we could run the optimization problem with closed form agent level updates, that is very compatible for implementation for the energy communities. And for our proposed loss allocation model, we utilize the marginal loss factor as a factor that allows us to fairly allocate the network losses among participants using, as I said, the marginal loss factor. That is the sensitivity factor based on the consumption of the electricity in different nodes to the total system losses. That if I want to explain it step by step, in the first step, we calculate the network power losses from energy trading using the on-chain power flow formulation. We formulate the power loss calculation, and then we calculate the marginal loss factors based on the output of the on-chain power flow and the flowing power through the lines and the voltages of the nodes. And then we identify the participants that contributing to loss increase or reduction. In the peer-to-peer energy trading, we can have both the positive loss as the increasing in the total loss, or negative loss, that means the reduction in the total loss. That it means the benefit for the market participants that contribute in the reducing the system losses. And then we allocate loss cost or benefit proportionally based on the energy trading price. We had the uniform price from the automated market maker based batch auction as the price function that we had. And based on the allocated loss or benefits among the market participants, we can update the final energy price that shows their contributed loss in the energy trading. And finally, we have a summary of numerical results here. We implemented our model in the IEEE 33 bus radial distribution network with 1,000 households at market participants. And we implement our on-chain power flow model based on the output of the automated market maker based batch auction energy trading. And in this figure that we have, we showed the accuracy of model compared to the AC power flow. As we can see, for the power flow difference in lines, it's less than 1% difference. And for the voltage magnitude, it's even less than 0.1% difference between our proposed model and AC power flow. And the average loss deviation was around 2.5% for these two power flow approaches. This result shows that our proposed model has high accuracy with significantly lower computational complexity. And also these two figures in the below shows that our proposed model using the corrective action model that we proposed, we can restore voltage magnitude and line flow through the feeders, that we can have a fully feasible approach after correction or adjustment of the consumption and generation. Yes, thank you. Thank you for your attention.
Thank you so much, Hossein. Any question online or in person? It was such a kind of informative web cafe. I hope that we could have more, the communication, like interaction between audiences. But I know that this is very technical. That might not be falling to everybody's interest, but it's good to have this sort of information online for everybody who wants to get familiar with the concept of the project. Yes, Alex.
Okay, thank you for your presentations. As a non-technical person, I'm not an electric engineer. I have maybe a more relaxed question. I wanted to ask you, what is it like for you as a academic team at a university with your teaching and research duties? What is it like to, on top of all of that, run a Horizon project like this?
So at university and as a research partner with teaching, with research, intelligent project is specifically very unique because the research we are doing usually would be theoretical. but this research is gonna be something visible in practice, because the uniqueness comes from the fact we are testing and demonstrating or theoretical concepts in the real world. So this makes a huge difference with the ordinary academic work, actually.
Thank you.
Yeah, sure. Any other thoughts, comments, either technically, conceptually? Or theoretically? If not, we can, Alex, close this webcam, right?
Yeah, thank you for the exhaustive presentation.
So then with that, I'm happy to answer any questions offline. Feel free to reach out to University of Cologne. And thank you for your time and have a good day.